Hello, friend. Welcome to Science for Sleep. Whether you have joined us before, or you are discovering this quiet channel tonight, this is a place to slow the pace, learn something gentle, and allow the day to slowly fade into the distance. Tonight, we are entering the world of whales. Far out at sea, the first sign of a whale may be nothing more than a dark curve appearing through the water. A smooth back rises for a few seconds. Then a burst of warm air leaves the top of the animal's head. From a distance, it can look like a fountain of seawater. But most of the visible cloud is not water being sprayed from the whale's lungs. It is warm, damp breath, meeting cooler air above the ocean. Much like the small cloud that can appear when a person breathes outside on a cold morning, moisture condenses into tiny visible droplets. A little seawater may also be carried upward from around the blowhole, along with mucus and natural oils from the whale's respiratory passage. The exact shape of the blow can sometimes offer a clue about the species below it. A blue whale often produces a tall, narrow column that may rise roughly 30 feet into the air. A humpback whale usually creates a shorter and rounder cloud. A North Atlantic right whale has two separate blowhole openings, and its breath can form a wide V shape when seen from the front. If you enjoy these quiet journeys, you're welcome to subscribe. And if it feels natural, to leave a comment sharing where you're listening from tonight. It helps others find this calm corner of science, one sleepy listener at a time. After the exhalation, the whale takes in fresh air with remarkable speed. Unlike a human, it does not breathe through its mouth. Its breathing passage is separated from the passage used for eating, helping prevent seawater and food from entering the lungs. Powerful muscles open and close the blowhole, forming a tight seal before the animal sinks below the surface again. Every whale must repeat this journey back to the air. A fish can draw oxygen from water using gills. A whale cannot. It may spend nearly its entire life surrounded by seawater, but its lungs still require the same oxygen found in the atmosphere above it. This is one of the most important facts about whales. They are not fish that happen to grow unusually large. They are mammals whose bodies were rebuilt for life in the ocean. They breathe with lungs. They maintain a warm internal body temperature. They give birth to live young. Mothers produce rich milk that allows their calves to grow quickly. Whales also possess the 3 tiny middle ear bones found in other mammals, although their hearing system has been heavily modified for life underwater. Even traces of hair remain. Some whale calves are born with short, whisker-like hairs around the mouth, especially near the tip of the lower jaw. Most of these hairs disappear as the calf grows, leaving only small pits where they once developed. The shape of the whale's movement also carries evidence of its mammalian past. A fish usually moves its tail from side to side. A whale drives its tail flukes upward and downward. Its spine bends in the same general direction as the spine of a running land mammal. The movement has been transferred into water, where each powerful stroke sends the animal forward. In the blue whale, that movement carries the largest body known to have lived on Earth. The longest blue whales can reach about 100 feet, similar to the length of a commercial passenger aircraft. The largest individuals may weigh more than 300,000 pounds. Their hearts can be roughly the size of a small motorcycle, and their main blood vessels are wide enough to carry enormous volumes of blood through the body. Yet even an animal of this size remains tied to a thin boundary at the ocean's surface. A blue whale may disappear for several minutes while feeding or traveling, but it must eventually rise again. Its blowhole reaches the air. The seal opens. Warm breath leaves the lungs. Fresh air enters. Then the opening closes. The back rolls beneath the surface, and the whale returns to a world where it cannot breathe. That repeated movement between water and air is older than any living whale. The blowhole on top of the head is the modern end of a nose that once pointed forward. Long before whales crossed entire oceans, their ancestors walked on four legs beside rivers and shallow coastal waters. The position of a whale's blowhole records a journey across the skull. In the earliest whale ancestors, the nostrils still opened near the front of the snout, close to the place where a dog or deer breathes today. Over millions of years, those openings shifted farther back. The change shortened the path between the surface and the lungs, allowing an aquatic animal to breathe while exposing only the highest part of its head. Fossils preserve several stages of that movement. They also reveal how legs became less important. Hearing changed, and the spine gradually took over the work of swimming. This transformation began during the Eocene epoch, a warm period in Earth's history that lasted from about 56 million to 34 million years ago. Much of the land that is now Pakistan lay close to shallow seas, river channels, and coastal wetlands. Around 48 million years ago, an animal called Pakititus lived in that region. Its name means the whale from Pakistan. Pakititus was roughly 6 feet long, though known species varied in size. It had 4 working legs, weight-bearing ankles, and a long skull with nostrils near the tip. Seen from a distance, it would not have resembled a modern whale. Its body was built for land, and it may have searched along streams for fish or other small animals. The clearest connection to whales was hidden inside its skull. Pakititus possessed a thickened ear bone called the involucrum. This unusual structure surrounds part of the middle ear and appears in every known cetacean. The animal group that includes whales, dolphins, and porpoises. The bone suggests that hearing was already beginning to change, even while the animal still walked on solid ground. A few million years later, Ambulocetus carried the transition farther. Its name means walking whale. Fossils from Pakistan show an animal around 10 feet long with powerful limbs, large feet, and a heavy tail. Ambulocetus could support itself on land, though its movements may have been slow and awkward. In water, the same body became more effective. The hind legs pushed against the water, while the spine bent upward and downward. That movement resembles the vertical motion still used by whales today. Ambulocetus probably lived somewhat like a crocodile, waiting in rivers or shallow coastal water before lunging toward prey. Its ears also show stronger adaptation to underwater sound. Dense bones helped limit vibrations passing through the skull, making it easier to separate useful sounds from surrounding noise. Later forms spent a growing share of their lives in water. Rhodotetus lived about 47 million years ago. Its pelvis was more weakly attached to the spine, reducing the ability of the hind legs to support full body weight. The feet were long, and their shape may have supported webbing. Its tail and flexible back likely supplied more of the forward thrust. Each useful change also created a cost. A body becoming better at swimming usually became less capable on land. By roughly 37 million years ago, Dorodon had crossed that limit. It lived entirely in the sea. Its forelimbs had become flippers, while its hind limbs were tiny and unable to carry the body. The nostrils had moved partway back along the skull, closer to the position of a later blowhole. Dorodon reached about 16 feet in length and swam through warm seas that covered parts of present-day Egypt. The much larger Basilosaurus lived during the same general period. Some individuals grew longer than 50 feet. Its narrow body stretched through the water, powered by a flexible spine and a tail region that probably supported flukes. Small external hind limbs remained near the pelvis. They still contained recognizable thigh, knee, and foot bones, though they could no longer support walking. Those limbs may have helped during mating, before eventually shrinking farther in later whales. Near the end of the Eocene, whale feeding also began to change. Gigantism lived around 34 million years ago in waters near Antarctica. It retained teeth, yet grooves and blood vessel channels in its upper jaw suggest soft tissues were developing around the gum line. These structures may represent an early stage on the path toward Baleen, though the exact feeding method remains debated. No single generation suddenly became a whale. Small changes accumulated across millions of births. Nostrils shifted along the skull. Forelegs broadened into steering surfaces. The pelvis loosened. The hind limbs shrank, and the spine became the main engine of movement. Life in water kept reshaping the same mammalian framework, one inherited structure at a time. Inside the broad flipper of a living whale, the bones of an ancient foreleg remain. A single upper arm bone connects to two forearm bones. Below them sit wrist bones and long rows of finger bones. The arrangement matches the basic pattern found in a human arm, a dog's front leg, or the wing of a bat. On the outside, thick skin and connective tissue hold these bones inside a flattened paddle. The joints have far less freedom than a human wrist or hand. That stiffness helps the flipper resist the pressure of moving water. A humpback whale uses especially long pectoral flippers, which can reach almost 1/3 of its total body length. Small bumps along the leading edge help water move across the flipper without separating too quickly from its surface. This allows a humpback to turn more sharply than its heavy body might suggest. The front limbs provide control, while most forward power comes from farther back. Large muscles running along the spine narrow into the tailstock, the strong section just before the flukes. With every swimming stroke, the spine bends upward and downward. The muscles pull the flukes through the water, producing lift in much the same way that a wing produces lift in air. The flukes themselves contain no bones. They are built mainly from dense layers of connective tissue that hold their shape under heavy force. The spinal column ends before reaching them. At their center, the two flukes meet at a small notch. Their wide surface pushes against a large volume of water with each stroke. A blue whale's tail can span more than 20 feet from tip to tip. Even at a slow traveling pace, that broad structure can move a body weighing well over 100 tons. The legs that once helped early whales walk followed a very different path. External hind limbs disappeared as they lost their role in swimming. Small pelvic bones remained buried inside the body of modern whales. These bones no longer attach to the spine in the strong, weight-bearing way seen in land mammals. They now provide attachment points for muscles connected with reproduction and other internal structures. Rare whales are born with tiny external hind limb remnants. Such cases occur when old developmental instructions become active during growth in the womb. They offer a rare visible reminder of structures that usually remain hidden. Other projecting body parts also became smaller or moved inward. Whales have no external ear flaps. Sound reaches their hearing system through specialized tissues in the head and jaw instead. Male reproductive organs can be drawn into the body, while the mammary glands of females lie beneath slits in the skin. A smooth outer shape reduces drag, which is the resistance created as a body moves through water. Water is more than 800 times as dense as air, so even a small projecting structure can increase the effort required for swimming. Buoyancy solves another problem by supporting the animal from all sides. On land, the weight of a large whale would press heavily against its own organs and chest. In water, that mass is spread across the body. The ocean supports the same enormous size that would become dangerous if the animal remained stranded on a beach. Permanent immersion also creates a constant struggle with heat. Water carries warmth away from the body much faster than air. A whale protects its core with blubber, a thick layer of fatty tissue beneath the skin. Depending on the species and body region, this layer may measure from roughly 2 inches to more than 12 inches thick. Blubber stores energy gathered during productive feeding seasons. A migrating humpback may rely on those reserves while traveling thousands of miles and eating very little. The layer also helps shape the body into a smooth form. Heat still needs careful control in the flippers and flukes, where thick blubber would interfere with movement. Arteries carrying warm blood outward lie close to veins bringing cooler blood back toward the body. Heat passes between them before too much can escape into the water. This arrangement is called countercurrent heat exchange because blood flows in opposite directions through nearby vessels. When the whale needs to release extra heat, circulation near the skin can increase. When warmth must be conserved, more heat remains within the returning blood. Beneath the whale's calm outline, old bones have changed jobs. Hidden muscles move immense surfaces, and blood vessels adjust to the temperature of the sea. The same rebuilt body soon divided into 2 branches, each shaped by a different way of locating and capturing food. About 34 million years ago, the whale family divided along a feature that still shapes every meal taken today. The change can be seen most clearly inside the mouth. One branch became the baleen whales, known scientifically as mysticetes. The other became the toothed whales, or odontocetes. Those formal names describe 2 broad groups that share the same ancient mammalian origin, while using the ocean in very different ways. Baleen whales include the blue whale, humpback whale, fin whale, grey whale, right whale, bowhead whale, sei whale, and minke whale. Instead of functional adult teeth, these animals carry rows of flexible filtering plates that hang from the upper jaw. Most baleen whales also have 2 external blowhole openings placed side by side on top of the head. When the whale surfaces, both openings release air together. This can help produce the wide, divided blow seen in right whales. The toothed branch includes sperm whales, beaked whales, belugas, narwhals, killer whales, dolphins, and porpoises. Members of this group usually possess one external blowhole. They also grow teeth, though the number and shape vary greatly. A sperm whale may carry more than 20 pairs of large teeth in its narrow lower jaw. Some beaked whales have only 2 teeth that become visible in adult males. The long tusk of a male narwhal is an enlarged tooth that grows forward through the upper lip. These differences reflect the kind of food each branch pursues. A blue whale may swim into a dense swarm containing millions of krill. Krill are small, shrimp-like animals that often gather in thick patches. The whale takes in a huge volume of seawater, then strains the krill through its baleen. A bowhead whale can move slowly with its mouth open, filtering tiny copepods from cold Arctic water. Copepods are small crustaceans, often only a few millimeters long. Grey whales use another form of filter feeding. They commonly roll onto one side near the seafloor, draw mud and water into the mouth, and trap small animals such as amphipods against their baleen. The toothed whales usually approach food one animal at a time. Sperm whales pursue squid and deep water fish. Orcas may hunt salmon, seals, or other whales, depending on the population and the feeding traditions learned within it. Belugas eat fish, worms, and animals living along the seafloor. Many dolphins chase schooling fish close to the surface. Teeth help grip slippery prey, while the tongue and throat move the captured animal toward the stomach. Chewing is limited in many species. Large pieces may be swallowed whole. Sound also developed differently between the two branches. Baleen whales often produce low-frequency calls. Low sounds have long wavelengths, allowing some of them to travel great distances through water under suitable conditions. Blue and fin whales can produce calls near or below the lowest tones that many humans can hear clearly. Humpbacks add more varied moans and repeated song patterns. Toothed whales commonly produce higher frequency sounds. Whistles can maintain contact between nearby animals. Short, sharp clicks provide information about surrounding objects and prey. By measuring the returning echoes, a toothed whale can locate food, even when darkness or cloudy water limits vision. This ability is called echolocation. Everyday language often treats dolphins and whales as completely separate animals. Biology places them on the same cetacean family tree. All dolphins belong to the toothed branch, including the killer whale, which is the largest member of the dolphin family. Common names developed from appearance and human tradition, rather than from a strict scientific boundary. Body size also crosses the familiar labels. The dwarf sperm whale may measure less than 9 feet long, while an orca can exceed 30 feet. A minke whale belongs to the baleen branch, even though some individuals are smaller than the largest toothed whales. The division rests in ancestry and anatomy, rather than size alone. Each branch gained access to a different kind of abundance. Toothed whales could search for separate prey hidden across open water or deep darkness. Baleen whales could harvest enormous numbers of small animals whenever currents and seasons gathered them together. That second strategy required whales to lose the adult teeth their ancestors once used for biting. In their place grew a filtering system that eventually supported the largest animal ever to live. Inside the mouth of a baleen whale, hundreds of dark plates hang from the upper jaw. They stand side by side in 2 long rows, one along each side of the mouth. Each plate is made mostly from keratin, the same tough material found in human fingernails and hair. The outer edge remains firm and smooth. Along the inner edge, the plate wears into a dense fringe of fibers. Together, those fibers form a flexible filtering surface. Baleen grows throughout the whale's life. Its lower edge is constantly rubbed by the tongue and moving water, which helps create the fine bristles used to trap food. A damaged section can slowly be replaced as new material grows downward from the gum. The plates differ greatly between species. In a blue whale, they may measure close to 3 feet long. A bowhead whale can carry baleen longer than 13 feet, the longest found in any living whale. The shape of those plates matches the food being collected. A whale feeding on tiny prey needs a finer filter than one capturing larger fish. The basic feeding cycle begins when prey-filled water enters the mouth. After the jaws close or partly close, the tongue and throat reduce the open space inside. Water is pressed outward through the gaps between the plates. Small prey remain caught against the fringed inner surface. The tongue then gathers the trapped animals and carries them toward the throat. A whale may repeat this movement many times while crossing a productive feeding area. Right whales and bowhead whales use especially long and narrow baleen. Their feeding method is often called skim feeding. The whale swims forward slowly with its mouth open, allowing a steady flow of water to enter near the front and leave through the sides. The long plates hang close together, while very fine fibers trap copepods. Copepods are tiny crustaceans, and many species are only a few millimeters long. A bowhead may travel through Arctic water, containing millions of them. Its curved lower jaw and high arching upper jaw create a large filtering chamber, allowing it to feed without taking separate lunging mouthfuls. Grey whales use a different part of the ocean. They often descend to shallow seafloors along the Pacific coast and roll onto one side. Suction draws mud, sand, water, and small animals into the mouth. The whale then pushes the sediment outward through relatively short, coarse baleen. Amphipods are among the common prey left behind. These shrimp-like animals live in tubes or burrows within the seabed. Feeding grey whales can leave long pits and clouds of disturbed sediment across the bottom. Many individuals favor the right side while feeding, and the baleen on that side may show heavier wear. Rorquals use shorter plates combined with a throat that can expand dramatically. This group includes blue whales, fin whales, humpbacks, sei whales, and minke whales. The name rorqual comes from a Norwegian word linked to the grooves running along the underside of the throat. Those grooves allow the mouth floor to unfold when the whale takes in a large volume of water. The baleen becomes the final barrier through which that water must pass. Humpback whales add learned behavior to this equipment. In some populations, one or more whales dive below a school of fish and release bubbles while swimming in a circle. The rising bubbles form a loose wall around the prey. Fish often gather more tightly toward the center, making the school easier to capture. A humpback may then swim upward through the concentrated group with its mouth open. This behavior is commonly called bubble net feeding. It has been studied in places such as Alaska and the Gulf of Maine. Some whales perform it alone. Others coordinate their movements, with different individuals producing bubbles, calling, or rising through the center. The exact pattern varies between regions and social groups. Young whales can learn local techniques by spending time near experienced feeders. Many humpbacks never use a bubble net at all. They may lunge through krill, strike fish with their tails, or feed near the surface using other methods suited to local prey. Baleen therefore works as part of a larger feeding system. Plate length, fiber fineness, jaw shape, swimming speed, and learned behavior all influence what the whale can capture. The loss of teeth opened access to food available in numbers far too great to chase separately. A single feeding event could collect thousands of small animals in a few seconds. Among the rorquals, the filter handled only the final part of that event. Before the water could be forced back out, the whale first had to take an enormous piece of the surrounding ocean into its mouth. A rorqual begins its feeding rush before the mouth opens. The whale first lines up with a dense patch of krill or schooling fish. Its tail drives the body forward until it may be moving at roughly 4 meters per second, close to 9 miles per hour. That speed sounds modest beside a fast boat, yet the moving body can weigh more than 100 tons. Opening the mouth too early would waste much of that momentum. Water is heavy, and forcing it aside creates drag, the resistance that slows anything moving through it. A whale swimming continuously with its mouth open would spend enormous amounts of energy. The lunge therefore happens as a short, carefully timed event. As the whale reaches the prey, its lower jaws rotate downward. The mouth may open to an angle approaching 90 degrees. The left and right halves of the lower jaw are joined at the front by flexible tissue rather than a rigid bony connection. This allows the jaws to spread slightly apart as the mouth expands. Along the underside of the body, dozens of pleated grooves run from the chin toward the belly. These folds lie close together when the whale is swimming normally. During a lunge, they unfold like the fabric of an opening bag. The floor of the mouth stretches downward and outward while water rushes inside. Muscle, blubber, and elastic tissue form this expanding pouch. In a large blue whale, its outer circumference may increase by around 150%. The throat can swell until the animal briefly looks wider through the front half of its body. The whale's tongue also changes position. In rorquals, the tongue can flatten and partly turn inward as water fills the mouth, making more room for the incoming load. This movement helps create a chamber capable of holding tens of thousands of liters. A large blue whale may engulf around 80 cubic meters of water during a strong feeding lunge. That is about 80,000 liters. Depending on the whale's size and the exact shape of the mouthful, the mass of the engulfed water can match or even exceed the mass of the whale itself. Such expansion must remain coordinated. Near the front of the lower jaws sits a specialized sensory organ surrounded by nerves and blood vessels. It detects pressure and movement as the jaws rotate. Information from this area appears to help the whale control how quickly the mouth opens and how far the throat expands. Without that feedback, the incoming water could place damaging forces on the jaw joints and soft tissues. The nerves serving the tongue and expanding throat have their own unusual structure. Ordinary nerves tolerate only limited stretching before their fibers become damaged. In rorquals, nerve fibers lie folded inside thick, elastic outer coverings. As the throat expands, those folds straighten. Tests on whale nerve tissue found that some samples could stretch by roughly 75 to 115% before breaking. This allows the nerves to remain connected while the surrounding tissue changes size dramatically within a few seconds. The feeding lunge also changes the whale's speed. Once the jaws open, the animal begins collecting water rather than simply moving through it. Drag rises sharply. The body slows as the mouth fills, even while the tail may continue to beat. Researchers have attached suction cup tags to whales to measure these changes. The instruments record depth, movement, speed, and body angle. Their data show a clear pattern of acceleration before the lunge, followed by strong slowing during engulfment. When the mouth is full, the jaws begin to close. Muscles in the throat and tongue reduce the size of the pouch. Water is pressed outward through the baleen plates. Krill or fish remain trapped against the fringed inner edges. The whale swallows the collected prey, then prepares for another pass if the patch remains rich enough. A single lunge may last only several seconds, followed by a longer period of filtering and repositioning. The entire process depends on timing. The whale must approach at a useful speed, open near the densest part of the prey patch, and take in enough food to repay the energy spent accelerating. A poorly placed lunge still fills the mouth with water. It simply brings in too little nourishment. The expandable throat gave rorquals access to feeding events unmatched by any other animal. Its value depended completely on the contents of each mouthful. Only an ocean capable of gathering tiny prey into thick, predictable swarms could support a body built to feed this way. A feeding strategy this demanding could succeed only where the sea gathered enough food into a small enough space. Whales had already been living in water for tens of millions of years before truly gigantic baleen whales became common. Early members of the group were much smaller than a modern blue whale. Some were closer in length to a large dolphin or a small bus. Fossil evidence suggests that baleen whales longer than about 10 meters became widespread only around 4.5 million years ago. By then, the basic filtering equipment had existed for far longer. The delay shows that baleen alone could not create a giant. The surrounding ocean also had to change. During the last several million years, Earth's climate became cooler and more strongly divided into seasons. Ice sheets grew and retreated. Sea levels rose and fell. Coastlines shifted as shallow seas opened, narrowed, or disappeared. These changes altered the movement of water and the places where marine food became concentrated. One of the most important processes was upwelling. In an upwelling region, wind pushes warm surface water away from a coastline or open ocean boundary. Colder water then rises from below to replace it. That deeper water carries nutrients such as nitrate and phosphate, which have accumulated from sinking waste and decaying organisms. Once those nutrients reach sunlit water, microscopic organisms called phytoplankton can grow quickly. Phytoplankton use sunlight to make food through photosynthesis, much like plants on land. They form the base of many ocean food webs. Tiny animals called zooplankton feed on them. Krill are part of this drifting animal community, though many species can also swim and gather into large swarms. Fish feed on the plankton, and whales arrive where the entire chain has become unusually dense. Productive upwelling occurs in places such as the waters off California, Peru, Namibia, and Western Australia. Around Antarctica, seasonal sunlight and nutrient-rich currents support immense blooms of phytoplankton. Antarctic krill feed on that growth and may gather in swarms stretching across many square kilometers. Within the thickest parts, thousands of krill can occupy a single cubic meter of water. That difference in density decides whether a lunge is worthwhile. A blue whale moving through scattered krill would still have to accelerate its enormous body. Its mouth would still open, the throat would still expand, and tens of thousands of liters of water would still need to be filtered. Too few krill would leave the whale with an energetic loss. A compressed swarm changes the calculation. One accurately placed lunge can collect hundreds of thousands of small animals. Repeated lunges through the same patch can provide enough energy to build thick blubber and support months of travel. Cooling climates also made marine productivity more seasonal. High-latitude seas can become extremely rich during spring and summer, when long daylight returns and melting ice opens more water to sunlight. During winter, those same regions may become dark, stormy, or covered by sea ice. Food therefore appears in powerful bursts, rather than remaining evenly spread throughout the year. Large bodies are well suited to this pattern. A giant whale can store enormous amounts of energy beneath its skin. Its long shape also allows efficient travel once it reaches a steady cruising speed. This makes it possible to feed intensely in one region, and later migrate thousands of miles toward warmer breeding waters. Greater size also increases the amount of water a rorqual can engulf during each lunge. The mouth and throat grow faster in volume than the energy cost of moving the body. A larger whale can therefore gain more food from a rich prey patch than a smaller whale using the same basic method. Scientists continue to study the exact causes of whale gigantism. Climate cooling, stronger upwelling, changing currents, and new migration patterns probably work together. Different whale lineages also reached large size separately, suggesting that several regions and feeding styles created similar opportunities. No single ocean event suddenly produced the first giant. Changing conditions repeatedly favored animals able to travel farther, store more energy, and take larger mouthfuls. Over many generations, those advantages carried several baleen lineages beyond 10 meters. Fin whales reached lengths greater than 70 feet. Bowhead whales developed massive bodies suited to cold Arctic seas. The blue whale eventually approached 100 feet and more than 300,000 pounds. Its size rests on a chain that begins far below the whale itself. Wind moves surface water. Deep nutrients rise into sunlight. Phytoplankton multiply, krill gather, and seasonal feeding grounds form. When any major part of that chain shifts, the largest body in the ocean must shift with it. The conditions that allowed a whale to become enormous also made that whale dependent on a limited number of exceptionally rich places. A blue whale approaching a feeding ground does not begin by opening its mouth. It first searches for the thickest part of the krill layer. During daylight, many krill descend into darker water to avoid predators. Whales may follow them hundreds of feet below the surface, then use changes in speed and body angle to line up a feeding pass. Researchers can observe these movements with temporary suction cup tags attached to the whale's back. The instruments record depth, acceleration, direction, and the rolling motion of the body. A feeding lunge appears as a clear sequence. The whale speeds up, rotates toward the prey, and opens its mouth only when the dense patch is close enough. That timing matters because a blue whale can expend a great deal of energy moving its enormous body. A mouthful filled with scattered krill would provide too little food to repay the effort. Inside a rich swarm, the same movement can capture hundreds of thousands of small animals. The advantage grows with body size. A larger rorqual has a wider mouth and a throat pouch capable of holding far more water. The volume of the feeding apparatus increases faster than the energy needed to move the animal through one lunge. Studies comparing rorquals of different sizes suggest that the biggest species can gain more energy from each successful feeding event than smaller whales using the same general method. A blue whale may consume several tons of krill during a productive day. Each krill is usually only a few centimeters long. The whale's survival therefore depends on countless small bodies being gathered by currents, temperature, and food into layers dense enough to find. Between lunges, the whale must manage oxygen with equal care. A temporary electrocardiogram tag was attached to a blue whale off the coast of California during a study published in 2019. An electrocardiogram measures the electrical activity that controls each heartbeat. While the whale was diving, its heart commonly slowed to an average minimum of about 4 to 8 beats per minute. For brief periods, the rate fell as low as 2 beats per minute. That slow rhythm helps reduce oxygen use while the animal remains below the surface. The heart rate changed during different parts of the dive. It increased during demanding movements such as feeding lunges, then slowed again as the whale glided or rested between efforts. Once the animal returned to the surface, its circulation shifted rapidly. During breathing periods, the heart accelerated to roughly 25 to 37 beats per minute. Fresh oxygen entered the lungs while blood moved quickly through the body. Within a short series of breaths, the whale prepared for another descent. These changes show how close extreme size brings an animal to physical limits. The heart must pump blood through a body that may stretch almost 100 feet from head to tail. A higher rate supports fast oxygen replacement at the surface. A lower rate preserves the stored supply during a dive. Even small changes in activity can alter the balance. Size also affects movement. A blue whale can travel efficiently once it settles into a steady pace, making long journeys between feeding regions possible. Sharp turns require more space than they do for a smaller whale. Acceleration demands force from immense muscles, while every feeding lunge creates a powerful wall of drag. Heat presents another challenge. Swimming muscles produce warmth, especially during repeated lunges. Cold seawater removes some of that heat, though the thick blubber that protects the whale from chilling can also slow heat loss. Blood flow near the flippers, flukes, and skin helps release excess warmth when the body becomes active. Reproduction adds a slower cost. Blue whale pregnancy lasts close to a year. A mother usually produces one calf, then nurses it for several months with extremely rich milk. Years may pass before she gives birth again. A population of blue whales therefore replaces lost adults gradually, even when food is plentiful. The largest body ever known succeeds through a narrow exchange. Dense prey supplies enough energy for growth and migration. Slow heartbeats extend the time available underwater. Seasonal feeding allows blubber to accumulate before long journeys begin. A shift in currents can move krill away from a familiar feeding area. Warmer water may change the depth or timing of a swarm. Reduced prey density forces the whale to spend more energy searching, while gaining less from each lunge. The same size that brings exceptional rewards also creates an exceptional daily requirement. Baleen whales answered the challenge of ocean feeding by gathering enormous numbers of prey in a single mouthful. Far below the light, toothed whales followed a different path, locating one moving target at a time through sound. As a toothed whale descends, the colors of the ocean begin to disappear. Red light fades first because water absorbs its longer wavelengths near the surface. Orange and yellow weaken below it. Blue light travels farther, giving clear tropical water its familiar color, though even blue eventually becomes too faint to guide a hunter. By about 650 feet, the whale has entered the twilight zone. Sunlight remains as a dim glow above, while the water below appears increasingly dark. Near 3,300 feet, the deep ocean begins, and sunlight no longer reaches it. Many toothed whales continue hunting well inside this darkness. Some pursue squid that give off flashes of light. Others follow fish whose dark bodies blend into the surrounding water. Vision may help at close range, yet sound provides information long before the prey becomes visible. A toothed whale begins by producing a click inside its head. Air moves through a group of passages beneath the blowhole. Specialized tissues within those passages press together and separate, creating a sharp pulse of sound. These structures are sometimes called phonic lips because their movement resembles the action of human lips, producing a brief pop. The air is kept inside the nasal system and recycled, allowing the whale to continue clicking without releasing bubbles or using another breath. The sound then passes through the melon, a rounded mass of fatty tissue in the forehead. Its shape can change slightly as surrounding muscles contract. Different kinds of fat within the melon carry sound at different speeds. Together, these layers help focus the click into a beam directed ahead of the whale. The beam is narrower than sound, spreading equally in every direction. That focus allows more acoustic energy to reach a target and improves the detail in the returning echo. A sperm whale uses a much larger sound-producing system. Its enormous head can form roughly 1/3 of its body length. Inside it lies the spermaceti organ, a long chamber filled with waxy oil. Sound travels through this region and reflects between structures in the head before leaving as an intense click. Some sperm whale clicks are among the loudest biological sounds ever measured. A click continues through the water until it meets something with a different density. The surface of a squid, the scales of a fish, or the hard shell of a crustacean can reflect part of the sound toward the whale. Specialized fatty tissue along the lower jaw receives those returning vibrations. The jaw directs them toward the middle ear and inner ear, where sensory cells convert the movement into nerve signals. The delay between the outgoing click and the returning echo provides distance. Sound travels through seawater at roughly 4,900 feet per second, though the exact speed changes with temperature, depth, and salt content. An echo returning almost immediately comes from a nearby object. A longer delay places the target farther away. Other parts of the echo add more detail. A strong return may come from a large target or a hard surface. Changes in frequency can reveal movement toward or away from the whale. The pattern of reflected energy may help distinguish a fish from surrounding water or separate one animal from a nearby group. The whale also receives echoes through two ears, positioned within the skull. Small differences in arrival time and intensity help identify direction. This process is called echolocation because the animal locates objects through echoes. It creates a stream of distance and movement information shaped by sound. As the whale approaches prey, the rhythm changes. Clicks that began with wider gaps are produced more rapidly. Each new echo updates the target's location. During the final seconds of pursuit, the clicks accelerate into a fast series known as a buzz. In sperm whales, researchers sometimes call this sound a creak because it resembles a rapidly turning wooden hinge when played through a speaker. The faster rhythm becomes useful when prey darts sideways or changes speed. A long pause would allow the animal to move between updates. Closely spaced clicks provide a more continuous record of the chase. Suction cup tags placed on toothed whales have recorded these patterns during real hunts. The tags measure depth and body movement, while underwater microphones capture each click. When a whale twists sharply or accelerates, a feeding buzz often appears at the same moment. Researchers can therefore identify likely attempts to capture prey even when the entire hunt takes place far beyond human sight. The darkness below the surface holds outlines made from returning sound. Each click reaches forward, and each echo adds a small piece of the surrounding space. The whale follows that acoustic trail deeper, where the growing pressure and the long distance from air place every part of its body under stricter control. At the surface, a sperm whale prepares for a dive with several minutes of steady breathing. Its blowhole sits on the left side of the head, producing a low angled burst rather than a straight vertical column. The animal may take 20 or more breaths, while its blood and muscles restore their oxygen supply. Then the back bends, the tailstock rises, and the broad flukes lift clear of the water. That final movement marks the beginning of a steep descent. Within a few minutes, the whale passes below the depth reached by ordinary sunlight. The water grows colder as pressure increases around the body. A typical feeding dive may descend to about 2,000 feet and last close to 45 minutes. Some dives continue much farther. Recorded sperm whales have reached depths beyond 6,000 feet, while the longest descents can keep an animal underwater for more than an hour. Much of that time is spent traveling rather than actively chasing prey. The whale may glide during part of its descent, allowing gravity and the compression of air spaces to reduce the work required. Its regular echolocation clicks often begin after it reaches deeper water. These clicks may be spaced about half a second apart as the whale scans ahead. Each sound travels outward, reflects from an object, and returns through the lower jaw. The pattern creates a changing record of animals scattered through the darkness. When a possible target appears, the whale adjusts its direction. A rapid burst of clicks begins during the final approach. Researchers call this faster sequence a buzz or creak. The closely spaced echoes help track prey that may twist, accelerate, or drop through the water. A buzz often lasts only a few seconds. Afterward, the whale may return to slower searching clicks before beginning another chase. Human observers cannot follow these hunts with ordinary cameras. The events take place in darkness under hundreds of meters of water. Scientists reconstruct them with temporary tags attached by suction cups to the whale's skin. A tag may record depth, body angle, acceleration, and sound. Hydrophones, which are underwater microphones, can also listen from research vessels or fixed stations. When a tag records a sharp turn at the same moment as a feeding buzz, the pattern suggests that the whale has closed on prey. Several such events may occur during one deep dive. Squid form a major part of the sperm whale's diet. The famous giant squid belongs to that diet, though it is far from the whale's only meal. Most hunts involve smaller and more common deep water species. Armhook squid, flying squid, and other soft-bodied animals may be swallowed whole. Sperm whales also take fish living far below the surface. Remains found in stomachs have included deep-sea sharks, rays, and bottom-dwelling fish. The teeth along the lower jaw can grip prey, but suction may perform much of the final capture. Powerful movements of the tongue and throat draw water and the animal into the mouth. The broad head helps support the sound system, rather than serving as a simple biting weapon. Males and females often hunt in different regions. Adult males can travel into cold waters near Norway, Alaska, and the edges of Antarctica. Females and young usually remain in warmer tropical or subtropical seas. A large male may exceed 50 feet and weigh more than 40 tons, allowing it to store enough oxygen for long, deep dives. Smaller females still reach impressive depths, though average dive patterns can differ with body size, region, and prey. Beaked whales carry deep diving even farther from human view. Cuvier's beaked whales have been recorded below 9,000 feet. One documented dive lasted more than 3 hours and 40 minutes, though such an extreme duration is unusual. These animals often remain quiet near the surface. Their echolocation clicks begin only after they have descended several hundred meters, possibly reducing the chance that predators such as killer whales will hear them from above. A sperm whale eventually turns upward after its deep search. Clicking may stop during part of the ascent. The animal rises through water that slowly brightens, though the surface remains far away. After 40 minutes or longer, its back finally appears again. A strong exhalation clears the lungs, followed by repeated breaths that restore the body for another descent. Those few visible minutes form only a small part of the daily cycle. Most feeding activity occurs beneath the reach of light, where sound reveals prey but cannot supply oxygen. The whale must power every click and every pursuit from the reserves carried down from the surface, then return before those reserves run too low. The oxygen carried into a dive is spread throughout the whale's body. The lungs hold part of it, though they are only one piece of the system. Much of the supply travels in the blood, attached to a protein called hemoglobin. Hemoglobin gives blood its red color and carries oxygen from the lungs toward organs and tissues. Whales generally have a large volume of blood for their body size, allowing more oxygen to circulate before the next breath. Their muscles contain another oxygen-holding protein called myoglobin. Myoglobin stores oxygen directly inside muscle cells, close to the places where it will be used. Diving mammals often have far more myoglobin in their muscles than land mammals. This high concentration can make the tissue appear unusually dark. A sperm whale descending toward deep water prey therefore carries oxygen in several connected stores. The lungs provide the first supply. Blood moves oxygen around the body. Muscle tissue keeps some available for local work during swimming and pursuit. Once the blowhole closes, the body begins managing those stores more carefully. Breathing stops, and the heart rate usually falls. This slowing is called bradycardia, meaning a heart rate below the normal active level. The change can begin before the animal has traveled very far beneath the surface. It is flexible rather than fixed. A whale swimming hard may maintain a faster heartbeat than one gliding quietly. The rate can increase during a chase, then fall again when activity becomes less demanding. Blood flow also changes. Vessels leading towards some muscles, the skin, and less urgent organs can narrow. This process is called vasoconstriction. A smaller amount of blood reaches those areas, while circulation continues toward the heart and brain. The muscles can then rely more heavily on oxygen stored in myoglobin. This selective circulation stretches the time before the most sensitive organs face a shortage. Pressure adds a different challenge. For every 33 feet of seawater, the surrounding pressure increases by about 1 atmosphere. At 3,300 feet, the pressure is close to 100 times greater than at the surface. Gas-filled spaces are affected strongly because gas can be compressed. A whale's chest and airways are built to change shape during descent. Flexible ribs allow the chest to compress. As pressure rises, air moves away from the tiny air sacs where oxygen normally enters the blood. Those sacs are called alveoli. The air is pushed toward stronger upper passages where the walls are better able to tolerate compression. Eventually, parts of the lung may collapse in a controlled way. This limits further exchange of gases between the lungs and blood at great depth. Reducing gas exchange matters because nitrogen can dissolve into blood and tissues under pressure. If too much nitrogen enters and the animal rises in an unusual way, bubbles may form as pressure falls. The problem resembles decompression sickness in human divers. Whales have several adaptations that reduce this risk, including lung compression and controlled circulation. Evidence from stranded animals has shown that gas bubbles and tissue damage can still occur under some conditions. Their bodies manage pressure with remarkable skill, while remaining subject to the same physical laws as every other air-breathing animal. The chemical balance also changes as a dive continues. Oxygen falls as cells use it. Carbon dioxide rises as a waste product of metabolism. Whales tolerate higher carbon dioxide levels than humans can comfortably endure. Their blood also contains buffering chemicals that slow changes in acidity. During intense activity, some muscles may begin producing energy with little oxygen. This creates lactate, a substance that accumulates when muscle cells work beyond the oxygen available to them. Much of that lactate remains within the muscles while circulation is reduced. After the whale surfaces, blood flow increases and carries it toward organs that can process it. Recovery therefore continues after the first breath. The whale may remain near the surface for several minutes, taking repeated breaths while oxygen levels rise and chemical balance is restored. A long dive is managed across the whole body. The heart changes pace according to effort. Blood vessels direct a limited supply toward the organs with the greatest immediate need. Muscles draw on oxygen stored inside their own cells, while the chest gradually compresses under the weight of the sea. Every movement draws from reserves that cannot be renewed until the surface is reached. That dependence continues during feeding journeys and long migrations. It also remains during the quiet periods when the whale's body needs rest. Rest creates a special problem for an animal that must keep reaching the air. A human can sleep for hours while breathing continues automatically. The chest rises and falls without any deliberate movement toward a surface. A whale rests inside water, where the blowhole must remain clear, and each breath requires the body to reach the boundary above. Drifting too deeply could delay the next breath. Rolling into the wrong position could place water over the blowhole. Remaining completely unaware for a long period could also separate an animal from its group or leave it exposed to approaching danger. Cetaceans have developed a form of rest that allows part of the brain to sleep while other functions continue. Cetaceans are the group containing whales, dolphins, and porpoises. In several well-studied dolphins and smaller toothed whales, electrical recordings show slow-wave sleep appearing in one half of the brain at a time. Slow-wave sleep is a deep resting state marked by large, gentle waves of electrical activity. During this state, nerve cells become less active and the brain uses less energy. The other half remains in a more alert condition. After a period of time, the two sides can exchange roles. This pattern is called unihemispheric slow-wave sleep. Unihemispheric means that one cerebral hemisphere, or one half of the upper brain, is sleeping. The arrangement allows neurological rest to occur without the animal becoming completely disconnected from its body and surroundings. One eye may remain open, while the opposite side of the brain stays more active. Dolphins swimming in a group can keep the open eye directed toward nearby companions. They may continue moving slowly, surfacing at regular intervals while one side of the brain rests. The swimming itself can remain simple and repetitive. Some dolphins circle a pool in the same direction for long periods. Others float near the surface or move in loose formation beside members of their group. Large whales cannot usually be brought into laboratories where brain activity can be measured directly. Researchers therefore study visible behavior, breathing rhythm, body position, and movement recorded with tags. Humpback whales have been observed resting almost motionless near the surface. Their backs may remain visible while they breathe slowly every few minutes. This behavior is often called logging. because the whale resembles a dark log floating in the water. Mother and calf pairs may rest close together, with the younger animal positioned beside the adult's body. Some whales continue slow travel during periods that appear restful. Their strokes become less frequent, and the route may remain unusually straight. Sperm whales display one of the most distinctive resting postures. Groups have been observed hanging almost vertically in the water, with their heads near the surface and their tails pointing downward. The whales remain close together and move very little. These quiet periods often last around 10 to 15 minutes before the animals become active again. One study using movement recording tags found that sperm whales spend only a small share of the day in these motionless resting events. The exact amount of true sleep remains difficult to measure because stillness alone does not reveal what every part of the brain is doing. Scientists also remain cautious when applying findings from dolphins to every large whale species. Direct electrical measurements have mostly come from animals such as bottlenose dolphins, belugas, and porpoises under controlled conditions. A blue whale traveling through the open Pacific may rest in a different pattern. Baleen whales and deep-diving toothed whales face different demands, and even individuals of the same species may change their rest according to age, migration, feeding, or the presence of a calf. Rapid eye movement sleep is another area of uncertainty. In humans, this stage is linked with vivid dreaming, relaxed muscles, and quick movements of the eyes beneath closed lids. Cetaceans show very little of this sleep stage in many direct measurements. Long periods of muscle relaxation would be difficult for an animal that must keep swimming or control its position in water. Brief, rapid eye movement-like episodes may occur in some species, though researchers have not found one universal pattern. Newborn cetaceans create an even greater challenge. Dolphin and killer whale calves may swim almost continuously beside their mothers during the first weeks after birth. The mother also remains unusually active during this period. Rest may occur in short, partial episodes while the pair stays in motion and maintains contact. As the calf develops stronger swimming control and better insulation, longer periods of calmer behavior can appear. Sleep in whales, therefore, combines several needs within the same hours. Brain tissue must recover while breathing continues at the surface. Body temperature requires steady control, and social contact may need to be maintained in dark or open water. Even during the quietest periods, part of the animal remains linked to movement around it. Much of that surrounding activity reaches the whale through vibrations traveling across the sea. Water carries a constant mixture of vibrations. A resting whale may hear waves breaking far above, rain tapping against the surface, or ice shifting along a cold northern coast. Some sounds begin much deeper. Underwater earthquakes send low vibrations through the seafloor. Volcanic activity can produce rumbles that travel across entire ocean basins. Fish create knocks, grunts, and drumming sounds by moving muscles against internal structures. Small crustaceans called snapping shrimp close one claw so quickly that a bubble forms and collapses with a sharp crack. A busy colony can create a steady background hiss. Other whales add calls, whistles, and clicks to the same underwater space. Human activity now contributes propellers, engines, construction, military sonar, and repeated pulses used to study layers beneath the seabed. all of these sounds can overlap. The ocean carries them far more effectively than light. Sunlight weakens as it passes through water, while many sounds continue well beyond the distance that an animal could see. Sound travels through seawater at roughly 4,900 feet per second. That is more than 4 times its speed through air. The exact speed changes with temperature, pressure, and salinity, meaning the amount of dissolved salt. Warm water usually carries sound faster than cold water. Greater pressure at depth also increases its speed. These changes can bend a sound wave as it moves between layers. A call may curve downward, turn upward, or spread toward the seafloor. Some of its energy reflects from rock, sand, ice, or the ocean surface. The shape of an underwater valley can channel sound. A shallow bank may scatter it. In parts of the open ocean, a layer called the deep sound channel allows low-frequency calls to travel especially far. Sound entering this zone is repeatedly bent back toward its center, instead of escaping quickly toward the surface or bottom. Under favorable conditions, a powerful low call may remain detectable across hundreds of miles. Baleen whales make frequent use of the lower end of the acoustic range. Many of their calls fall below 5 kHz. A kilohertz means 1,000 sound vibrations each second. Blue whales and fin whales can produce tones close to the lowest frequencies heard by humans, with some calls dropping below ordinary human hearing. Low-frequency waves have long wavelengths and lose energy slowly in deep water. They are useful for maintaining contact across distance, especially when whales are widely separated during travel or feeding. Humpback whales also produce low moans, along with higher cries and repeated song units. Right whales use rising calls that sweep upward in pitch. Researchers often call one of these an upcall. It can help nearby whales remain aware of one another, even when waves, darkness, or distance hide the body producing it. Toothed whales use a wider range of higher frequencies. Whistles often support social contact within a pod. Echolocation clicks are much shorter and can reach tens or even hundreds of kilohertz, depending on the species. Higher frequencies provide finer detail because their shorter wavelengths reflect from smaller objects. A harbor porpoise can use very high clicks to detect small fish. A sperm whale relies on powerful, lower frequency clicks, suited to longer range searching in deep water. Each type of sound trades distance for detail in a different way. A signal also depends on the noise surrounding it. A whale call remains useful only when another animal can separate it from the background. Masking occurs when one sound covers another, because they share similar frequencies or arrive at similar times. The low rumble of a large ship can overlap with the calls of baleen whales. A single vessel may pass in minutes, while major shipping routes create almost continuous noise. Pile driving during coastal construction sends strong repeated impacts through the water. Seismic surveys used to map rock beneath the seabed release intense pulses at regular intervals. Military and research sonar can cause some whales to change direction, interrupt feeding, or leave an area. The effect depends on sound level, frequency, distance, species, and what the animal is doing at the time. A feeding whale may respond differently from a resting mother with a calf. Noise does not need to cause direct injury to matter. A quieter call may become harder to hear. The useful distance between two animals can shrink, A whale may call more loudly, repeat itself, or shift the pitch. Some groups alter their movement when familiar areas become noisy. The ocean therefore functions as an acoustic habitat. Currents, depth, weather, living animals, and human machines continually reshape what can be heard. A whale moving through that space receives information from far beyond the visible horizon. Certain calls provide simple contact. Others are arranged into long patterns that are remembered, repeated, and gradually changed by the whales that hear them. Among humpback whales, some calls are arranged into patterns that can last for many minutes. A single sound may be a low moan, a rising cry, or a short pulse. Researchers call these smallest pieces units. Several units repeated in the same order form a phrase. A group of related phrases creates a theme. The whale moves through several themes in a set order, then begins the full sequence again. That complete repeating sequence is known as a song. One performance may continue for 20 minutes before repeating. A male can sing for hours, cycling through the same basic arrangement while changing small details. The sound is produced without vocal cords. Air moves through structures connected to the whale's nasal passages, while the animal remains underwater. No cloud of bubbles needs to escape with every sound. This allows the singer to continue through a long performance before returning to the surface for air. Most complete humpback songs are produced by males, especially around tropical and subtropical breeding grounds. During a single season, males using the same breeding area usually sing broadly similar versions. A singer near Hawaii may follow nearly the same sequence as another male many miles away. The timing, pitch, and voice quality can differ between individuals, though the shared pattern remains recognizable. These common versions do not remain fixed from year to year. A phrase may grow longer. One unit can be replaced by a different sound. A theme may slowly change its position within the larger sequence. Small changes spread as males listen to one another and adjust their own performances. By the following breeding season, the population may be singing a noticeably updated song. This gradual change resembles a tradition being revised through repeated learning. No whale is born carrying one exact song for life. The pattern is heard, remembered, and reproduced. More dramatic changes also occur. Researchers studying humpbacks in the South Pacific have documented events known as song revolutions. During a revolution, a population's familiar song is replaced by a substantially different version over a relatively short period. The new arrangement may arrive from a neighboring population and then spread through local singers. Some of the clearest examples began along the eastern coast of Australia. New song types appeared there and later moved eastward across the South Pacific. Related versions were recorded among whales near New Caledonia. The cultural wave continued through Tonga and reached populations near American Samoa. Later recordings found connected song types around the Cook Islands and eventually French Polynesia. The full movement covered thousands of miles. A whale did not need to cross the entire Pacific carrying the song from beginning to end. Information could pass through several points of contact. Males from different breeding populations may meet on shared feeding grounds. Migration routes can overlap. A small number of traveling whales may also move between neighboring populations and introduce an unfamiliar pattern. Once local males begin copying it, the new song can spread rapidly. This eastward direction is especially interesting because the songs often moved from larger populations towards smaller ones. A version sung by many whales may have had more opportunities to reach neighboring groups. Researchers are still studying why a new pattern becomes popular enough to replace an older one. Novelty may attract attention. Changing the song could affect competition among males. A shared version may also help singers match the current social environment around a breeding ground. The exact purpose of the full song remains uncertain. Its close link with the breeding season suggests a role in reproduction. Females may listen to aspects of the performance, although direct evidence for female choice remains difficult to collect in the open ocean. Males may use song while spacing themselves apart or assessing nearby rivals. Several functions could operate at the same time. Recent studies have found that humpback songs contain repeating patterns that can be studied with some of the same mathematical tools used for human language. Frequently used sound pieces tend to appear in organized positions, and whales seem able to learn the structure of a changing sequence. These findings show complex cultural transmission. They do not provide a translation of the song or prove that humpbacks use human-style grammar. The science is strongest where recordings can reveal structure, change, and movement between populations. Meaning remains harder to measure. A humpback song can mark a place and season, while carrying traces of singers heard months or years earlier. Across the Pacific, one changing performance becomes shared knowledge. Sperm whales organize social information into much shorter patterns, using a handful of clicks to signal membership within groups that may remain connected for decades. Among sperm whales, the most stable relationships are usually found between females and their young. Several adult females may travel with calves and juveniles in a long-lasting social unit. These groups can remain connected for many years, even when individuals spread apart to feed. A whale may dive alone for squid, while another adult stays nearer the surface with a calf. Researchers have described this shared care as babysitting, although the behavior serves a practical purpose. A young calf cannot follow its mother on every deep hunting dive. Another female may remain close enough to guide the calf, protect it, and help maintain contact until the mother returns. Young males grow up within these units. As they approach adolescence, they gradually spend more time away from the females. Many eventually travel toward cooler, higher latitude waters, where larger males may feed for years before returning to warmer regions to breed. Females tend to remain in tropical and subtropical seas, maintaining relationships that can continue across much of their lives. Sound helps hold these societies together. The regular clicks used for hunting are long, powerful signals spaced for echolocation. Social exchanges often use shorter rhythmic patterns called codas. A coda may contain only a handful of clicks. The timing between those clicks creates a recognizable pattern, much like a rhythm tapped on a table. Two whales meeting near the surface may exchange codas while turning toward one another. The clicks can arrive in overlapping sequences, with one animal answering before the other has completely finished. Researchers record these exchanges with underwater microphones and temporary animal-borne tags. The rhythm can carry several kinds of information. Some coda patterns are strongly associated with particular individuals. Other patterns appear frequently within one social unit. A wider set of shared rhythms can identify a vocal clan containing many units spread across a large region. One well-known pattern in the Caribbean contains a regular series, followed by 2 closely spaced clicks. Researchers often call it the 1+1+3 coda because of its grouped rhythm. Members of the same clan use related identity patterns even when they live far apart and rarely meet every other member. Vocal clans can cover thousands of miles of ocean. In the Pacific, 2 clans may use some of the same feeding waters while continuing to produce different coda repertoires. Their ranges overlap, yet their sound traditions remain distinct. This suggests that geography alone does not determine membership. Young whales learn the rhythms used by the animals around them. Repeated association gradually places each individual inside a social tradition. The process resembles the spread of humpback song, though codas serve a different purpose. Humpback songs change broadly across a breeding population and season. Sperm whale codas help maintain identity during everyday social life. The patterns can remain stable for years while still allowing variation between individuals and families. Social learning also shapes behavior beyond sound. Female sperm whales may form defensive circles when threatened by killer whales. Calves are kept toward the center, while larger adults face outward. The group may remain tightly packed, using powerful tails and jaws to discourage an attack. Humpback whales provide another example, through feeding traditions. In the Gulf of Maine, some individuals strike the surface with their tails before lunging through schools of sandlance. This technique, known as lobtail feeding, spread through social connections after it was first documented in the 1980s. Whales that spent time near experienced feeders were more likely to adopt the same method. Other populations use bubble nets, shoreline feeding, or specialized movements suited to local prey. Biologists use the word culture for behavior that is learned socially and shared within a group. In whales, culture can include a vocal rhythm, a feeding technique, or knowledge of where to travel. The term describes how information moves between animals during life. It does not require cities, written records, or human-style institutions. A whale can still inherit useful behavior by watching, listening, and remaining close to experienced companions. This makes age important in a way that population numbers alone may not show. An older female may carry knowledge of feeding areas used during poor years. She may help guide younger whales through a migration corridor or respond to danger through behavior learned decades earlier. When such an animal disappears, her body is lost along with the relationships and practical knowledge linked to her life. Those connections become especially valuable when food lies far from breeding waters. A social group crossing the ocean must know when to leave, where to travel, and how to find productive water again. The timing of a migration can be as important as the route itself. A whale leaving too early may abandon a feeding ground before it has stored enough energy. A late departure can expose a calf to colder water or place the journey out of step with changing currents. For many populations, migration links habitats that provide different parts of the yearly cycle. Cold northern seas often supply the richest food. Warmer coastal waters can offer calmer conditions for mating, birth, and the first weeks of a calf's life. The eastern North Pacific grey whale follows one of the best-known routes. During spring and summer, many feed in the Bering, Chukchi, and Beaufort Seas near Alaska and the western Arctic. These shallow northern waters support dense communities of amphipods and other small animals living in seafloor sediment. A grey whale rolls onto one side, draws mud into its mouth, and filters prey through its baleen. The feeding season allows thick energy reserves to build beneath the skin. As autumn advances and Arctic daylight shortens, the whales begin moving south. Many follow the western coast of North America, passing Alaska, British Columbia, Washington, Oregon, and California. The route remains close enough to land that migrating whales can sometimes be seen from cliffs and beaches. Travel often continues at only a few miles per hour. Even at that steady pace, the distance accumulates day after day. The destination lies along the Pacific coast of Baja California in Mexico. Sheltered waters such as Laguna Ojo de Liebre, San Ignacio Lagoon, and the lagoons around Magdalena Bay serve as important breeding and nursery areas. A complete annual round trip commonly covers about 10,000 miles. Some tracked journeys have exceeded 14,000 miles, when the animal's full route and feeding movements are included. The same individual may repeat a broadly similar journey year after year. Memory probably contributes to this return, along with environmental cues encountered during travel. Coastline shape, water temperature, currents, sound, and possibly Earth's magnetic field may all provide useful information. No single navigation system has been shown to explain the entire route. Humpback whales create a second migration pattern across many parts of the world. Animals feeding near Alaska may travel toward Hawaii or Mexico. Southern Hemisphere populations leave waters near Antarctica and move toward tropical breeding regions around Australia, the South Pacific Islands, Africa, or South America. Certain humpbacks travel close to 5,000 miles between seasonal habitats. A journey of that length can take weeks. During travel, the whale may reduce feeding sharply or stop feeding for long periods. The energy required for swimming then comes from blubber built during the productive season. A pregnant female carries an additional cost. Her stored fat supports her own movement while the calf continues developing. After birth, those reserves help produce milk that can contain more than 30% fat. The calf gains weight rapidly, even when the mother has eaten little for months. Migration therefore operates as an exchange between places. Northern feeding grounds provide concentrated food during a limited season. Warm breeding waters support reproduction while offering much less nourishment for a giant filter feeder. The body carries energy from one region to the other. Not every whale follows the full pattern. Some grey whales remain along the Pacific Northwest during summer, instead of continuing to the Arctic. They belong to a smaller group, often called the Pacific Coast Feeding Group. Individual humpbacks may shorten a migration, skip a breeding season, or remain near a productive local food supply. Age, health, reproductive condition, and prey availability can all change the route. Environmental shifts also move the useful parts of the ocean. A warming current may alter where krill gather. Reduced sea ice can open northern water earlier, while changing the prey living beneath it. Whales may respond by arriving at different times or exploring unfamiliar feeding areas. Older animals that have experienced several poor years may carry knowledge of alternative routes and distant food sources. For a whale traveling alone or within a loose group, migration still connects many lives. Calls help maintain contact across water, where the bodies cannot be seen. Calves follow mothers along paths they may later repeat as adults. Feeding knowledge gathered in one season influences the timing of movement in the next. The scale is immense, yet the purpose remains practical. Food is gathered where the sea produces it most heavily. Stored energy carries the whale through thousands of miles of travel. For a female nearing the end of pregnancy, arrival in sheltered water marks the beginning of a far more demanding task. The long route finishes as a new whale takes its first breath. A pregnant grey whale entering a sheltered Baja lagoon has already spent weeks travelling south. The journey may have covered 5,000 miles from northern feeding grounds. During that time, the growing calf has drawn energy from reserves the mother stored beneath her skin during the previous feeding season. Birth takes place in water, often far from any solid surface. Many observed whale calves emerge tail first. This position may reduce the time the head is exposed before the rest of the body is free, though births are difficult to observe, and the pattern should not be treated as universal. Once released, the calf must reach air quickly. The mother stays close, swimming beneath or beside the newborn. Her body may help guide it upward during the first unsteady movements. Another female may also remain nearby in some species. Within moments, the calf's blowhole breaks the surface and opens for its first breath. That simple action requires several systems to work together. The calf must control its body position, close the blowhole before sinking, and return to the surface again before its limited oxygen supply runs low. Its muscles have never carried it through open water. The lungs have only just begun exchanging air. Early swimming can appear uneven, with short strokes and frequent surfacing. The mother matches this slower pace. A blue whale calf begins life at a scale larger than most adult animals. It may measure around 23 feet long and weigh close to 6,000 pounds at birth. Even with that size, it remains dependent on its mother for food and protection. Blue whale pregnancy is estimated to last about 10 to 12 months. A mother usually gives birth to one calf. Twins can occur, though they are extremely rare. The calf nurses for roughly 6 or 7 months. Whale milk contains far more fat than ordinary cow's milk. In blue whales, the fat content may reach 35 to 50%. The thick milk carries a large amount of energy in a small volume and does not spread easily into the surrounding water. The calf seals its mouth around the mammary slit, while the mother releases milk under pressure. Rapid growth follows. A young blue whale may gain more than 100 pounds in a day during its fastest period of nursing. By the time it is weaned, the calf may have doubled much of its original length and added many tons of body mass. That growth draws directly from the mother's stored energy. During migration and early nursing, she may eat very little. Her blubber supports milk production, while also meeting the demands of travel and her own metabolism. This investment limits how often she can reproduce. Blue whale births are commonly separated by 2 or 3 years. A female needs time to recover body condition before another pregnancy can succeed. Sperm whales follow an even slower schedule. Pregnancy lasts roughly 14 to 16 months. The calf may continue nursing for several years, even after it begins sampling solid food. Females often produce only one calf every 5 to 7 years. Young sperm whales remain close to adult females while learning the rhythms of their social unit. They cannot follow their mothers on the deepest feeding dives. Other females may stay near the surface with them, while the mothers descend. Milk alone does not prepare a calf for adult life. A young whale must refine the timing of each breath and learn how its body responds to waves and currents. Social calls become familiar through repeated contact. Migration routes are experienced by following an older animal over thousands of miles. Feeding skills develop gradually. A humpback calf may watch its mother approach fish or krill before attempting similar movements. A young sperm whale spends years building the oxygen stores and diving ability needed for deeper hunts. Calves also depend on the condition of the water around them. Rough seas can separate a young animal from its mother. A weakened female may produce less milk. Ships, fishing lines, and changing prey conditions can affect survival long before the calf reaches maturity. Being born large provides some protection from heat loss and smaller predators, though size cannot replace time spent learning. Whale reproduction therefore proceeds slowly. One pregnancy occupies many months. A single calf may require years of care. The interval before another birth can stretch across a large part of a human childhood. Each surviving calf carries a substantial share of the population's future. Under favorable conditions, that dependent newborn may eventually cross oceans, raise calves of its own, and remain alive for many decades. In a few species, the life beginning beside one mother can continue for longer than an entire human lifetime. Measuring the full life of a whale is difficult because few individuals are watched continuously from birth to death. A researcher may photograph an adult for the first time without knowing whether it is 20 years old or 80. The animal may disappear into open water for months, cross an ocean basin, and return years later carrying a few new scars. Scientists therefore estimate age from tissues and physical records that change in predictable ways. In many toothed whales, the teeth preserve growth layers. New material forms over time inside or around the tooth. When a tooth is cut into a thin section, alternating bands may become visible under a microscope. Researchers count these layers in much the same way that growth rings are counted in a tree. The exact rate must be studied separately for each species, because one visible band does not always equal 1 year. Baleen can also preserve a record of time. As a baleen plate grows downward from the gum, its chemical makeup changes with the whale's diet and location. Sections formed on northern feeding grounds may contain different chemical signals from those produced during migration or fasting. Reading these changes can reveal repeated seasons across several years of the animal's life. Some baleen whales carry another record inside their ears. A waxy plug slowly builds within the ear canal. Alternating light and dark layers can mark changes between feeding and migration. Scientists have counted these layers after a whale's death to estimate its age. The wax can also preserve traces of hormones and pollutants absorbed decades earlier. A small structure inside the eye provides a different biological clock. The central lens begins forming before birth. Proteins near its center remain in place for the rest of the whale's life. Over time, their building blocks gradually change shape through a chemical process called amino acid racemization. Measuring the amount of change can provide an age estimate, especially in very old animals. Photographs offer a living record. Humpback whales can be identified by the shape and markings beneath their tail flukes. Right whales carry rough patches of pale tissue called callosities on their heads. The pattern is different on each animal. When the same whale appears in photographs across 40 or 50 years, researchers gain a confirmed minimum age even when its birth was never witnessed. Bowhead whales have pushed these methods farther than any other mammal. They live in Arctic and subarctic waters around Alaska, Canada, Greenland, and Russia. Their huge heads can break through sea ice thick enough to block smaller whales. Some individuals exceed 60 feet in length and carry the longest baleen plates of any species. Evidence suggests that bowheads can live beyond 200 years. The first clues sometimes arrived in an unexpected form. Whalers found old stone or metal weapon fragments buried deep inside the blubber of living bowheads. A few fragments came from hunting tools no longer used for many decades. The whales had survived the original strikes and continued living long enough for tissue to grow around the objects. Stronger age estimates came from eye lens chemistry. In one major study, several bowheads were estimated to be more than 100 years old. The oldest individual was placed near 211 years, though every estimate carries a range of uncertainty. A whale reaching that age could have been born during the early 19th century. Its lifetime might span the rise of steamships, the height of industrial whaling, and the arrival of modern satellite tracking. Such longevity creates a biological puzzle. A very large animal contains far more cells than a mouse or a human. Each time a cell divides, its DNA must be copied. Damage can occur during copying or after exposure to chemicals, radiation, and ordinary metabolism. More cells and more years should create more opportunities for dangerous errors. Large, long-lived animals have evolved stronger systems for controlling those risks. Recent research on bowhead cells has found unusually effective repair of double-strand DNA breaks. These breaks occur when both sides of the DNA molecule are cut. Poor repair can rearrange genetic material and increase the chance of cancer. Bowhead cells appear especially skilled at restoring this damage accurately. One protein involved is called cold-inducible RNA-binding protein. Bowheads produce unusually high levels of it. Laboratory experiments suggest that the protein supports careful DNA repair and may help cells survive damage. This work is still developing. It does not provide a ready-made treatment for human aging. It reveals one way a long-lived mammal maintains its cells across an extraordinary span of time. A whale surviving for 2 centuries can learn routes through changing ice, remember distant feeding areas, and remain part of a social population across many generations. Throughout that long life, every movement also carries nutrients and stored material from one part of the ocean to another. Those nutrients continue moving long after a whale has swallowed its meal. A feeding whale breaks down krill, copepods, squid, or fish inside a multi-chambered digestive system. Proteins and fats support the animal's muscles, blubber, and growing tissues. Material the body does not use eventually returns to the water. This waste can contain nitrogen and phosphorus, two nutrients needed by microscopic ocean plants. Iron may also be present, especially in regions where very small amounts can limit growth. Many whales feed below the surface, sometimes hundreds of feet down. They must regularly return to the air, so much of their waste is released closer to the sunlit upper ocean. This movement carries nutrients upward from darker feeding depths. Phytoplankton living near the surface can then absorb some of that material. Phytoplankton are tiny organisms that use sunlight to produce energy. Their growth supports zooplankton, which then feed fish and larger animals. A nutrient released by a whale can therefore re-enter the food web close to where sunlight makes growth possible. Scientists often call this process the whale pump. Physical upwelling raises deep, nutrient-rich water through currents and wind. Whales create a smaller biological version by feeding in one layer and releasing digested material in another. The effect varies with location, species, season, and population size. A sperm whale may carry nutrients upward after hunting squid in deep water. A baleen whale, feeding below a krill layer, may surface repeatedly between lunges. In the Southern Ocean, iron is especially important because large areas contain plenty of other nutrients, but relatively little usable iron. Whale waste can return some iron to the upper water in a form that phytoplankton can absorb. The whale may later feed on krill that grew from the same broad food web. Nutrients also move sideways across the planet. A humpback can build its body reserves in Antarctic waters, then travel thousands of miles toward a tropical breeding ground. Grey whales carry material south from Arctic feeding areas toward the coast of Mexico. During migration, whales continue breathing and producing waste. Pregnant females also transfer stored nutrients into developing calves and later into milk. A scientific analysis published in 2025 described this movement as a great whale conveyor belt. The phrase refers to nutrients carried from productive high-latitude seas toward warmer regions where many whales breed and give birth. Some of the transported material enters the water through waste. Another portion supports calves that begin life far from the feeding grounds where their mothers built those reserves. The total movement was far greater before industrial whaling reduced many large whale populations. Even so, scientists remain careful when estimating the effect. Whales influence nutrient cycling and carbon movement, though restoring their numbers cannot solve climate change by itself. Their role works alongside currents, plankton, fish, seabirds, and countless smaller organisms. A whale continues affecting the ocean after death. When a large carcass sinks, it may descend thousands of feet before reaching the seafloor. This event is known as a whale fall. The body creates a sudden supply of food in a place where meals of that size are extremely rare. Large scavengers often arrive first. Deep-sea sharks, hagfish, and crabs can remove much of the soft tissue over months or years. Smaller animals then gather in the enriched sediment around the bones. Worms, snails, and crustaceans use the remaining scraps and the chemicals released as tissue breaks down. The final stages can last for decades. Whale bones contain large stores of fat. Bacteria, living without oxygen, break down some of this material and produce hydrogen sulfide. a chemical that other specialized microbes can use for energy. Entire communities develop around that process. Among the most unusual animals are Osedax worms. Their name means bone eater. They have no ordinary mouth or stomach. Root-like tissues grow into the bone, where helpful bacteria allow the worms to obtain stored fats and proteins. Different Osedax species can colonize the same skeleton at different times. A single carcass therefore connects several parts of the ocean during its existence. Feeding brings nutrients into the whale's body. Migration carries them across great distances. Waste returns some material to sunlit water, while death may deliver the remaining body to the deep seabed. This movement continues across years and, in long-lived species, across more than a century. When whale populations were heavily reduced, the ocean lost more than large animals. It also lost slow reproduction, learned roots, and a repeated flow of nutrients carried by bodies that took decades to grow. For thousands of years, coastal peoples hunted whales on a limited local scale. Communities in the Arctic, the North Pacific, and other coastal regions used whale meat, oil, skin, bone, and baleen for food, tools, shelter, and trade. These hunts were tied to season, weather, available boats, and the number of animals that could be reached from shore. Industrial whaling developed around a different goal. Whales became raw material for expanding markets, and each improvement in ships or weapons allowed hunters to travel farther and process more animals. Some species were easier to catch than others. Right whales moved relatively slowly near the surface and often traveled close to coasts. Their thick blubber produced large quantities of oil. Their long baleen plates could be cut into flexible strips, used in corsets, umbrella ribs, carriage springs, and other products before modern plastics became common. A dead right whale also tended to float. Hunters therefore described it as the right whale to pursue. By the 17th century, European fleets were hunting bowhead and right whales around places such as Spitsbergen and Greenland. As nearby populations declined, ships moved into more distant waters. American whalers later crossed the Atlantic, Pacific, and Indian Oceans in voyages that could last several years. Sperm whales became especially valuable during the 18th and 19th centuries. Their blubber produced oil used in lamps and machinery. Inside the enormous head lay spermaceti, a waxy substance that could be refined into bright burning candles and high-quality lubricants. A large sperm whale might yield many barrels of oil. The crews lowered small open boats from a sailing ship and approached the whale with hand-thrown harpoons. The method was dangerous and limited by wind, rowing speed, and the strength of the animal. Fast rorquals were much harder to catch. Blue whales and fin whales could outrun the small boats used by earlier hunters. Their bodies often sank after death, making recovery difficult. Technology changed that balance during the 19th century. The Norwegian whaler Sven Foyn helped develop a practical explosive harpoon during the 1860s. The weapon was fired from a cannon mounted on a steam-powered catcher boat. Its metal head opened inside the whale, while an explosive charge increased the chance of a rapid kill. Steam engines allowed the vessel to chase animals regardless of wind. Compressed air could be pumped into a carcass to keep it floating. Species that had once been too fast or too difficult to recover became profitable targets. industrial fleets followed whales into the Southern Ocean during the early 20th century. Antarctic waters held enormous feeding populations of blue, fin, humpback, and sei whales. Shore stations first processed carcasses near islands and coastal bases. Factory ships later carried the equipment needed to cut up whales and render oil while remaining at sea. By the 1920s and 1930s, a carcass could be hauled onto a large ship through a ramp in the stern. Crews worked across wide processing decks while smaller catcher boats searched for more animals. The fleet no longer needed to return to land after every kill. This system increased both range and speed. As one species became scarce, hunters shifted toward another. Blue whales were heavily reduced, followed by growing pressure on fin and sei whales. Smaller minke whales became more important after many larger species had already declined. The pattern appeared in one ocean after another. Slow reproduction could not match the rate of removal. A female whale might carry one calf for nearly a year, nurse it for months, and wait several more years before giving birth again. A factory fleet could kill dozens of whales in a short period. The population lost breeding adults far faster than new calves could survive to replace them. International regulation developed after the damage had become difficult to ignore. The International Convention for the Regulation of Whaling was signed in Washington in 1946. It created the International Whaling Commission, which was intended to manage whale hunting and conserve depleted populations. Early quotas often remained too high or were based on incomplete population estimates. Enforcement was also difficult across large stretches of open ocean. In 1982, the Commission voted to pause commercial whaling. The moratorium took effect during the 1985 to 1986 season. It remains the central international restriction on commercial whaling, although limited commercial hunts continue in some countries under formal objections, reservations, or separate legal arrangements. The end of large-scale industrial hunting gave several populations room to increase. Recovery began from very different starting points. Some groups still contained thousands of animals. Others had been reduced to a small fraction of their former numbers. The harpoon fleet had slowed, while ships, fishing gear, and industrial noise continued spreading through the same migration routes and feeding grounds. Protection gave some whale populations enough time to begin growing again. Several humpback groups increased greatly after large-scale commercial hunting declined. In the western South Atlantic, humpbacks that breed near Brazil recovered from only a few hundred animals to many thousands. North Pacific humpbacks also returned to feeding grounds where they had once become uncommon. Their recovery required decades because females usually raise one calf at a time. The growth of these populations shows what can happen when adult survival improves and enough calves reach maturity. Other whales began the same period with fewer animals, slower growth, or greater exposure to human activity. The North Atlantic right whale remains one of the clearest examples. These whales migrate along the eastern coasts of the United States and Canada. They feed mainly on tiny crustaceans called copepods, gathering where currents concentrate the prey into dense layers. Pregnant females travel south during autumn and early winter. Calves are usually born in shallow water from South Carolina to northern Florida between November and April. By 2026, the population was estimated at approximately 380 whales. Only about 70 were reproductively active females. Each female therefore carries a large share of the species' ability to recover. The 2025 to 2026 calving season brought a cautious reason for hope. Researchers identified 23 mother and calf pairs, the highest number recorded since 2009. 20 of the mothers had given birth in earlier years. 13 of those returning females had last produced calves during the 2021 or 2022 seasons. Their intervals between births were shorter than the recent average of roughly 7 to 10 years. A healthier right whale population would usually produce calves more often, closer to every 3 or 4 years. Food supply strongly affects that timing. Pregnancy and nursing require thick energy reserves. When copepods become harder to find, a female may need extra years to rebuild enough body fat for another calf. 23 births can help only when deaths remain low. For a population of fewer than 400, losing several adults can erase much of the gain from a productive season. Fishing gear creates one of the greatest dangers. Vertical ropes may connect traps or pots on the seafloor to floating markers at the surface. A whale swimming through the area can catch a rope in its mouth, around a flipper or across the tailstock. The line may tighten as the animal moves. Rope cutting into skin can create deep wounds and infection. Heavy gear adds drag, forcing the whale to spend more energy during every mile of travel. Feeding becomes harder, while a nursing mother may lose energy needed to support her calf. Some entanglements kill quickly. Others remain attached for months as the whale weakens. Many living right whales carry scars showing that they survived at least one encounter with fishing gear. Ships create a second major threat. Right whales often travel near the surface and may rest just below it. Dark skin and a low profile make them difficult to see from a moving bridge. A large vessel needs considerable distance to slow or turn. Collisions can break bones or cause severe internal injury. Propellers may leave long cuts across the body. Mothers and calves spend frequent periods near the surface, increasing their exposure along busy coastal routes. The danger moves as the whales move. During the last decade, changing ocean temperatures have altered where copepods become concentrated. Some right whales began spending more time in the Gulf of St. Lawrence in Canada. Fishing activity and vessel rules, designed around older distribution patterns, did not always cover these newer gathering areas. Managers have had to adjust closures, speed limits, and monitoring zones as whale locations change. Sea ice can alter bowhead habitat in the Arctic. Krill shifts affect humpbacks and blue whales elsewhere. A protected boundary remains useful only when it continues to overlap the animals it was created to protect. Recorded deaths also reveal only part of the loss. A whale killed far offshore may sink before anyone finds it. Research suggests that only about 1/3 of North Atlantic right whale deaths are documented. Population estimates, photographs, injury records, and sightings must be combined to identify animals that have quietly disappeared. Recovery therefore develops at different speeds in different waters. Some humpback populations now contain tens of thousands of animals. North Atlantic right whales remain close enough to extinction that every adult female matters. the appearance of 23 calves is meaningful progress. Their contribution will depend on whether those calves and their mothers can cross feeding grounds and shipping lanes safely for decades. Modern protection begins before the whale and the danger occupy the same patch of water. That requires finding animals whose bodies may be submerged and invisible long before a ship appears above them. Finding a whale before danger reaches it begins with an unusual problem. The animal may surface for only a few seconds, disappear for nearly an hour, and travel hundreds of miles before researchers see it again. A blue whale can cross an ocean basin. A right whale may move between feeding grounds in Canada and calving waters near Florida. Much of that journey takes place beneath waves that hide the body completely. Modern whale science therefore combines several incomplete records. A photograph may reveal identity. A tag can record one stretch of movement. An underwater microphone may hear an animal that remains too distant to see. Together, those pieces create a clearer account of where a whale has traveled and what it encountered. Photo identification is one of the longest used methods. The underside of a humpback whale's tail flukes carries a pattern of dark and light markings. Scars, damaged edges, and natural pigmentation allow researchers to recognize the same individual years later. Dorsal fins and saddle-shaped markings can identify killer whales. North Atlantic right whales carry rough pale patches on their heads, called callosities. Small crustaceans called whale lice live on these raised areas, making the patterns easier to see from a boat or aircraft. Catalogues now contain photographs collected across decades. A whale first recorded as a calf may later return as a mother with a calf of her own. Drones add measurements that ordinary photographs cannot provide. Flying above an animal, a drone can record the width of its body and the shape of its back. Researchers compare these measurements with body length to estimate physical condition. A thin whale may have struggled to find enough food, or may be spending large amounts of energy during migration and nursing. Repeated flights can show whether a mother loses weight while supporting a calf. Temporary suction cup tags gather a different kind of information. These instruments can contain depth sensors, accelerometers, hydrophones, and small cameras. An accelerometer measures changes in movement. It can reveal each tail stroke, body roll, feeding lunge, or sudden turn. Some tags have recorded heart activity, showing how circulation changes between deep dives and rapid breathing at the surface. After several hours, the suction cups release, and the tag floats upward for collection. Small biopsy samples can also be taken with specialized darts. A piece of skin and blubber may reveal sex, genetic relationships, hormone levels, diet, or exposure to pollutants. Each sample is small, while the information can connect an individual whale to a wider population. Sound remains especially valuable because listening can continue when human observers cannot. Passive acoustic recorders are underwater microphones left in place for weeks or months. They operate through darkness, rough weather, and long periods when no aircraft or research vessel is nearby. During the 2026 North Atlantic right whale calving season, recorders called sound traps were deployed between Hatteras, North Carolina, and Cape Canaveral, Florida. They were positioned roughly 10 to 50 nautical miles offshore. The devices listen for right whale upcalls, which rise in pitch over about 1 second. Months of underwater sound create an enormous amount of data. Computer systems can scan recordings and mark sounds that resemble known whale calls. Human analysts then examine the likely matches. This step matters because ship noise, other animals, and changing water conditions can produce similar patterns. Machine learning helps sort the material, while expert review protects against false detections. A confirmed call can lead to practical action. Mariners may receive a warning that whales are nearby. Vessels can reduce speed in areas where collisions are more likely. Fishing activity may be adjusted when whales enter waters filled with vertical lines. Rescue teams can prepare when an injured or entangled animal is identified. Environmental models add information about sea temperature, currents, plankton, and prey, helping researchers estimate where whales may gather before sightings begin. No single instrument captures an entire life. A photograph records a moment at the surface. A tag follows part of one day. A hydrophone detects a voice without always revealing the animal's exact identity. The clearest picture develops when these records overlap across many years. Far offshore, a dark back rises through the water. The blowhole opens, and warm breath condenses in the cooler air. That opening began as nostrils near the front of a land mammal's skull roughly 50 million years ago. The lungs below it carry oxygen into blood and muscle. A learned route brought the whale to this water, while distant feeding grounds supplied the energy supporting its body. Ships, ropes, changing currents, and human decisions now shape the conditions surrounding its journey. Within seconds, fresh air enters and the blowhole closes. The back rolls forward. The ocean surface settles above the descending body. A recorder may continue hearing its call after the whale has passed beyond sight, following the faint signal through water that still holds part of its story.